Well, good afternoon. Thank you all for joining us today in our conservation webinar series here hosted by the Iowa Learning Farms. I'm Liz Ripley. I'm the Conservation and Cover Crop Outreach Specialist with the Iowa Learning Farms, and I'll be our webinar MC today. So I'd like to welcome Brady Clausen, a graduate research assistant here at Iowa State University. He's going to be sharing with us some of his research entitled Circular Bioeconomy Strategies for Enhancing Soybean Plant Health. And if at any time you've got questions for Brady, feel free to enter those into the chat. And I would like to give a quick recognition shout out to our funders that help make this webinar series possible. And they include our Iowa Department of Agriculture and Land Stewardship, the Iowa Department of Natural Resources, the Iowa Nutrient Research Center, and the Leopold Center for Sustainable Agriculture. So again, thank you all for joining us today, and I will turn the virtual floor over to Brady. Thank you.
Thank you, Liz, for the introduction. Let me make sure my mic is on real quick. Okay, we're all good. Yeah, thank you, Liz, for the introduction. Again, my name is Brady Clausen. I'm a master's student here at Iowa State University studying sustainable agriculture, and I'm happy to be here with everyone to kind of present some work on my thesis surrounding circular bioeconomy approaches for improving soybean plant health. So a little bit about the project PIs and a couple of people I work with. So I am co-advised by Dr. Lisa Schulte-Moore and Dr. Leonore Leandro. And then we work very closely with Dr. Shantanu Bashki at the Bioeconomy Institute producing biochars. And so I'll dive into that here in a little bit. Today, I really wanted to focus on, what does an agricultural circular bioeconomy look like, and specifically maybe some key examples here in Iowa. And then following that, what is biochar and anaerobic digestate? How do they feed out of the agricultural circular bioeconomy, and how do they feed back in? Thirdly, I really want to get into, my specific research. This is a pretty big project. So, I'm only doing a little piece of the puzzle. So I'll specifically start to get into what I've been working on, a few previous field trials that set the foundation for kind of my research the past couple of years. And then, of course, some methods and results from those experiments I conducted. And then we'll kind of conclude and I'll give you guys some key points. So what is a circular bioeconomy? Essentially, the bioeconomy encompasses the production of renewable biological resources and their conversion into food, feed, bio-based products, and bioenergy. This definition can take many different types of examples, but I thought this one was the most clear-cut one. Essentially, the way I always think about it is, we're turning biological materials and we are adding utility or value to them for societal good. So what exactly does a circular bioeconomy look like in terms of agriculture and then also Iowa? So really, I like to start in the top right here with our feedstocks. So you have manure, food waste, of course, from like household, restaurant, grocery. And then we move into other organics like crop residues, energy crops, and perennial grasslands. So essentially, this is the organic matter that we are going to add that utility or value to. And in order to do this, we have to valorize it. Now, specifically, the project I work on, we are focused on, it's called Grass to Gas, and we are focused on the co-digestion of prairie switchgrass and winter rye with essentially beef cow manure, but we look at all manures across the board from different feedstocks. And so essentially we look at this idea of, okay, let's take these products and let's put them into two industrial pathways that valorize these products. So the first pathway is you have pyrolysis here. And so you can kind of see this fire emoji here and explains it pretty well. Essentially, we're taking that organic matter and we're burning it or thermochemically converting it. And out of this, we create bio oil, syngas, heat, and biochar. And then another pathway that this organic matter can go into is anaerobic digestion. So this kind of complements pyrolysis in a way. It's almost opposite, I think about it. So instead of burning the material, we're essentially composting it in the absence of oxygen, which produces biogas or methane. We clean that. And then it also produces a solid byproduct known as digestate. And these two processes or industrial pathways, pyrolysis and anaerobic digestion, ultimately their main use is to, again, valorize that material and turn it into products like fuel, electricity, and heat, again, that can be exported out to society or the region that these are in. Following that, again, I emphasized it a little bit. What's left over after these processes are taken underway is that we get these solid materials left over at the end. And so we could refer to these as co-products. So we have biochar, which is kind of a carbonaceous-like material, almost charcoal-like, very good for long-term carbon sequestration and kind of soil health properties, mainly soil structure. Following that, we have digestate. So we have this solid liquid separated nutrient dense material. So you can imagine this like slurry like material that has grasses and manure in it. And we take that and add it essentially kind of like a fertilizer back onto the field. So really where I'm going to focus my talk today is on the idea of using these co-products and applying them back onto the field. We don't have any, or at least my experiments weren't done in the field, but they were done in greenhouse. And so I'll be happy to share a little bit on those. Just to give everybody a little bit better idea of what these two things look like. On the left, you're seeing, of course, the biochar, charcoal-like material, a little dusty, can get a little dirty. I've had experience with that. And then digestate. So this stuff's going to be a little bit more smelly, but very nutrient-rich and dense. So where do we get this biochar from? The cool thing about our biochar is we use a novel pyrolysis system called allothermal pyrolysis. So usually during conventional pyrolysis, we exclude all of the oxygen. But what they found out at the BioCentury Research Farm here at Iowa State in Ames is that autothermal pyrolysis, so instead of taking the oxygen out, we induce just a little bit of oxygen, driving that partial oxidation of the material or the organic matter, which then supplies the heat needed for pyrolysis, hensing the name autothermal. It creates its own energy source. So overall, we get lower external energy requirements and cost overall. So the anaerobic digestate and where this comes from is from a commercial farm in southeast Iowa, Seavers Family Farm in Stockton, Iowa. So what you're seeing here is both the anaerobic digester and kind of the circularity of how this system works. So in the middle there where it says heat, just to the right of that, you're seeing two dome shapes, and those are the anaerobic digesters. So the manure and the bedding and the corn stover and the cereal rye and the food waste are all going to go into this digester, be composted, zero oxygen. We collect that gas. That gas gets cleaned, purified, and sent out to the natural gas grid. While you can see that arrow moving from those two domes out to the field with digestate, that solid product then gets put back into applied back onto the soy and corn rotations. So really what we were specifically focused on is to assess the impact of autothermal biochar and anaerobic digestate on the early stages of soybean growth. So during that springtime when the plants really need a lot of energy to get up and going to, either fight diseases or different environmental stressors, what are the impact of these amendments during that early growth? And then secondly, we were really interested in this idea of, okay, as soon as we start to add a stressor and start to complicate the biology of our system a little bit, what happens with both the biochar and anaerobic digestate in soil and the impacts of the soybean plant after being attacked under a pathogen like this? And can biochar and digestate help mitigate that a little bit? So before I kind of get into some of my experiments, just a little background information on, what is soybean sudden death syndrome? Essentially, it's a fungus known as Fusarium fertiforme, which during the springtime, when we have cool, compact conditions, the fungus is going to infect the root. From there, after the roots are infected, it releases a toxin that translocates to the leaf during the summer, midsummer time. And then around the time of harvest, we have chlorosis, necrosis, and early leaf defoliation. And so in the top left, that's kind of the picture you're seeing here. And then the bottom left, I really like this picture because it's a picture from just this past year, 2025, showing the latest harvest and what they were seeing for SDS here actually in Ames. So you can just kind of see the damage it could potentially do towards the senescence part of the soybean stage. Just to kind of give you an idea of like in the United States, what are the most important pathogens. And, sudden death syndrome is ranked number two among all significant diseases for soybean. So really just wanted to emphasize, we're not dealing with any rare pathogen or anything here, very widespread and very big problem. And big problem, mostly leading to yield loss, right? So at the end of the year, we seem to get around 30,000, yeah, 30,128 bushels of soybean are lost due to this disease. Just to add a little bit more relevancy to this, so what you're seeing is in 2010, there was an epidemic of this disease in Iowa specifically. And so they went out and started to look for where is it most severe in the state of Iowa. And so that's what you're seeing here on the map. And then coincidentally, the anaerobic digester where we source our digestate from is located in one of the most high severity areas. So again, just pulling that relevance to the commercial side of thing. And we think a lot of our research will have implications that can be directly impactful to the farmer, Mr. Sievers, of course, down in Southeast Iowa. I'm just going to take a minute here to kind of start to set the foundation for our work and kind of what two publications really started to kind of arise these questions out of us. So on the left, you're seeing adding anaerobic digestate to commercial farm fields increases soil organic carbon. So this was a group of people on the Grass to Gas project, not myself, but that worked on what is the impact of anaerobic digestate because they are applying that digestate onto the field currently in Southeast Iowa. So they went out there and were looking at carbon specifically, and they found that soils started at a 1.7% carbon, meaning that was below the 2% soil health threshold. And what they found is that digestate has the ability to raise the soil organic carbon by zero point 0.8 megagrams of carbon per hectare per year. Which is enough to exceed that 2% soil health threshold within 10 years. So you can see really the true impact here. Within 10 years, any given farmer may be able to increase their soil organic carbon and increase, this idea of reducing our agrochemical dependence as well, and potentially could act as a fertilizer. Although that's still being heavily studied and we can't answer that directly, but it's really cool to see at least the soil organic carbon being teased out. Moving to our right here, a little bit more focus on biochar. This was a study done here at Iowa State, and it focused on biochar in greenhouse and field studies, and they found that it differed by biochar type, the effects, but they found a really promising one that had a high fixed carbon content. So this is a high fixed carbon content, meaning it's just a more recalcitrant carbon that I'm talking about. And what they ultimately found is that biochar suppressed disease in both the greenhouse and field studies. So again, setting the stage that biochar has this potential to reduce disease. Okay, so now I'm going to move into my biochar section, kind of sort of experiments. We'll kind of work from left to right with this graph. So on your left, you have biochar. So we use three different types of feedstocks or biochar types. We had a control corn stover, an iron impregnated corn stover. So essentially we pre-treated the feedstock with an iron sulfate. And then we had a yellow pine feedstock for our biochar. So those are all three of our biochar types. We took those biochars and amended them all at 0, 20, 30, and 40 grams per kilogram. And we amended them into pasteurized soil. So we eliminate a lot of the background biological or microbiological noise. And then in order to get the disease into the system, we use a vector such as sorghum to inoculate the soil with. We amend the soil with that sorghum. And then, of course, if we're studying the idea of plant health performance in the absence of disease, those treatments did not receive the sorghum. And then after we mixed that all up in our pots, we then went ahead and planted Williams 82 soybeans. We planted 3 of those. And then after emergence, we thinned to just a single seedling. And then for the rest of the time, we watered. And then about 4 to 5 weeks, we took the experiment down and we analyzed plant growth parameters as well as disease severity parameters. So the next about 4 graphs are going to essentially all be the same, so you can interpret them the same. The only thing that's going to change is the y-axis. So currently right now on our x-axis, we have the increasing biochar rate, and you'll see that the 0 grams per kilogram is all the same in each feedstock because we had a shared control. And so you'll see that repeated over each feedstock. And so again, the biochar rate is on the x-axis. On the kind of top x-axis, we have it faceted by different biochar types. So we have corn stover on our left, the iron corn stover in the middle, and the yellow pine over to the right. And then our y-axis variable right now is plant biomass. So looking at the biomass produced by these plants, essentially hypothesizing more biomass, potentially more yield. Again, growth chamber conditions, but that's the idea. Essentially, overall, we found no effect of autothermal biochar out of any of them on plant growth or in terms of plant biomass. The only thing we found was it seems like there was an increasing plant biomass with the increasing rate of yellow pine. And then at the 40 grams per kilogram, we finally see a statistical difference from the control. So, of course, just showcasing that yellow pine seemed to promote plant biomass a little bit. And again, this is without the pathogen. So we're looking, no pathogen is present in these plants. We're just looking at baseline plant health performance. Again, a very similar graph, except we're doing root length now. I think the interesting thing here is essentially across all biochar types or feedstocks, we see an increase in root length. So we know that biochar seem to increase the biomass for yellow pine and then increases the root length for all the biochars. This is a very interesting one. So as we move from biomass to root length to plant height, now in plant height, we get a reduction. So we saw an increase in root length, but then a reduction in plant height. And this is suggesting maybe a potential energy allocation of the plant early, is that it starts to, especially when there's a sandier soil, which we were using, these plants started to exhibit less plant height and maybe allocated more energy towards root length growth. And then, of course, this is just the final slide, kind of captivating for no pathogen, basically baseline plant health performance. And you'll see that how the soil pH kind of changed based on the application of these different types. So you have corn stover on the left, which raised the pH, iron corn stover, which dropped the pH, and then yellow pine remained relatively comparable to the control, maybe a little bit of a elevated pH there. And so this really showcases, if we're going to be adding these biochars onto working or agricultural lands, we need to take in consideration their soil buffering mechanics, especially with iron corn stover. If the idea is to drop your soil pH, this may be able to sequester carbon and drop that pH. But if you don't want to do that, of course, that would be bad. So just really making sure we match amendment types and rates with what agronomic performance we want out on the land. So now I'm just switching gears just slightly. So the same experiments, the only thing we're doing is these treatments had the pathogen present. So there is a pathogen in the soil trying to infect the soybean. And what we see here is the graph is essentially set up the same way. We're faceted by corn stover, iron corn stover, and yellow pine. The top set of graphs, as you can see on the right, is going to showcase the root rot percentage. So the percentage of rot that we found on the roots at the end of the experiment. And then on the bottom, you see something called AUDPC, which stands for area under the disease progress curve. So essentially what this does is it takes all the foliar symptoms that we evaluated over time and turns it into one composite value, kind of giving us a value of disease severity in one composite value over time. So we don't have a line graph here, we have those composite values. So essentially, if there is more of an AUDPC, that means there's more foliar symptoms. Less AUDPC, less foliar symptoms. Overall, what we see here is that the 20 and 40 grams per kilogram of biochar tended to exacerbate disease severity. And we found that for all three of them. As we started to tease this apart a little bit more, we had complementary experiments that followed this, and it further demonstrated that corn stover and iron corn stover tend to increase root rot severity, if not disease severity overall, while yellow pines shows a marginal to no effect whatsoever on disease severity. And so I can't showcase all the data for our biochar experiments today, but I did want to showcase this one graph and then give you everyone a little bit more information on kind of some of the other stuff we've been doing. So overall, again, corn stover, iron corn stover, seems like anything corn stover based increases disease severity, while yellow pine largely shows that no effect. Okay, so now we're going to be switching gears a little bit into the digestate side of things. So, in the same kind of fashion, in the same way we set up the experiments, we have solid digestate on the left, only one type, so we don't have three types like the biochar, just one type from that commercial farm. And we amended it at 0, 10, 20, and 30 grams per kilogram to the same pasteurized soil, and we inoculated the soil the same. From there, we take a 200 ml sample and we dispense that into our pots. We then plant our soybeans and then do the same growth metric assessments and plant disease assessments at the end. I think this is pretty cool just because the commercial farm is actively doing this right now. So I wanted to draw a little parallel to the application rates I'm using in the greenhouse and how those relate out onto the field scale for application rates. So on our way left, we have application rate. We have 10 grams per kilogram. And as you move all the way to the right, you'll see that it translates to about a 13 megagram per hectare field rate. Of course, we're using some pretty generous assumptions here, but this is starting to give that idea a little bit. And the pounds per acre are just below that too, if anybody prefers seeing it that way. Following that, the 20 translated to 26 megagrams and the 30 translated to 39 megagrams. What I think is really cool about this is that the Sievers Farm has applied in its history anywhere from 6 to 55 megagrams of per hectare. So I think this is really cool that our greenhouse experiments kind of get through that whole range and showcase that whole range that they've applied out in the field. Again, just drawing even more parallel to what we're doing here and what's happening on the commercial side. So again, this is the digestate results when no pathogen is present. So just baseline plant health performance. And what we see overall is we see a linear increase of both biomass and root length, which are significant, but you can see they're pretty marginal overall. And this is probably just due to the idea of, we only grow these plants for about 4 to 6 weeks. So, there isn't probably a tremendous amount of time for the plant to start to allocate energy towards shoot growth. I would imagine and hypothesize over time, and as you get to, yield at the end of the year, that we would, see these treatments start to sparse a little bit more, and we would maybe see a little bit more biomass or root length gain. But still, even during early growth stages, this is really good to see. And so, again, marginal, but still positive. So just switching from now, that was the baseline plant health performance, and now we're looking at what happens when we add the pathogen in with the digestate. So the way this graph is set up is you have root rot on the top left, AUDPC in the top right, and reminder, that's just the foliar symptoms. And then on the bottom left, you have biomass and root length. I think the really cool thing here and what I want to emphasize is all of these parameters showed the same pattern for a quadratic response or a nonlinear dose response. So, for example, up in the top left, we have root rot. So we start with the control, and as we move down to the 10 grams per kilogram, we see a slight reduction, not statistically significant, but a slight reduction. And then from there, we start to see an increase in disease severity as we move up into the 30 grams per kilogram. And you'll see that same trend follows into the foliar symptoms. So again, we see that little dip at 10 grams per kilogram, and then it starts to quickly become more severe as we get into higher application rates. And it even starts to perform on the plant growth metrics we measured. So not only did we see that dip of root rot up here in the top left at 10 grams per kilogram, this was not statistically different from the control. But what we do see is an enhancement of biomass from that treatment. So no reduction in root rot, but we do see more biomass there. And then root length had a significant quadratic trend, just marginally though. And overall, we see those same trends. So it seems like higher rates of digestate seem to exacerbate disease, and while 10 grams per kilogram and under seems to mitigate disease, if not enhance plant performance when the pathogen is there. I really like this picture. This was just from one of our experiments, so we repeated this multiple times. But what you'll see here on the top left is the no amendment, and then on the right, moving from there, is the 10 grams per kilogram amendment, and then on the bottom left and right is the 20 and 30 respectively. And so essentially, I really like to show this top right graph where you see that the 10 gram per kilogram, it doesn't take much to be able to look at this picture and say, yeah, those plants have enhanced shoot and root growth. And so I think that's really cool. Even though we didn't see that reduction in root rot with the 10 grams per kilogram, we see an enhancement in biomass, which ultimately, and what we hypothesize would help the plant be able to fight that pathogen off. So just switching gears, this was going to be kind of our last set of experiments that I'll be going through. We really started to get interested in what happens when we start to put biochar and digestate together. Is there a synergy between the two? Do they operate or act better together than alone? And so we, in the same fashion of all the experiments I've kind of shown up to this point, we did just that. So on the left, we have our digestate. The biochar we chose was the yellow pine because it tended to show, no effect in terms of disease severity. And then the other kind of thing we added onto this experiment was the implementation of field soil. So in the previous experiments, we were using pasteurized soil. So the microbial background was kind of eliminated. Here we're using a full field soil from the Marsden rotations here in Ames. So we took that field soil, we took the digestate, we took the biochar, mixed it into the cup and amended it. And then in the same way, we inoculated the soil. Now, the treatments for this experiment included a control, so no amendment. The digestate applied at 10 grams per kilogram, a yellow pine biochar applied at 30 grams per kilogram, and then the combination of those two treatments, so digestate plus biochar, which resulted in a 40 gram per kilogram amendment rate. So we mixed all those up into the treatments, and then of course we added in the soybeans, thinned them, and then after about that 4 to 6 week mark, we started to evaluate. So this first set of graphs is going to show no pathogen. So there's no pathogen in these plants, just looking at baseline plant health performance. In the top left, you'll see root nodules. So this was a metric I added. I kind of found it interesting. As I moved from pasteurized to field soil, pasteurized had no root nodules present on any plants, never, ever. And then as soon as I got into field soil, there were root nodules. And so I started to quantify those. And what we see there is, the digestate and the combination of the two seem to help. Moving to the right, we have biomass. Bottom left, we have root length. And in the bottom right, we have plant height. So we're looking at, this idea of biochar and digestate on early plant growth, no pathogen present. And what we found is that you'll see that when we have biochar and digestate, we can improve the root nodules, the biomass, the root length, and the plant height. So biochar plus digestate amendment together really resulted in overall the greatest significant increase in these growth plant measurements. Okay, so now just switching gears just slightly, same experiment, only now this has the pathogen in the soil. So on the y-axis, we're looking at root rot percentage, and what you'll see is there was no effect. So looking at the difference between control, digestate, biochar, and the combination, they all had no effect on any disease severity. So we thought this was really cool, and cool meaning that these products are probably going to be applied onto the land. In terms of plant disease management, it's good to know that they have no effect. It's even better if they do have a positive effect, but even them having no effect is really good for integrated pest management, just to know we're not exacerbating anything, which we found at those higher rates could be potential. But here in the field soil, we didn't see any of that. And then following that, these are just the growth parameters of those diseased plants. So these were the plants that had the pathogen in the soil. So in the top left, we have biomass, top right, root length, bottom left is plant height, and bottom right is root nodules. And so in the experiments before, when there was no pathogen, we saw the biochar and digestate combination work the best. As we move into the pathogen being there, we see that it is the 10 grams per kilogram digestate amendment that seems to perform the best with the pathogen. So you see this increase in biomass, increase in plant height, and also an increase in root nodules. So again, when we put the pathogen in the soil versus when we don't has large implications for both what these products are doing to the disease. I'm just going to go through 3 slides and kind of just give some very overview key points of all the stuff I kind of just went through. Largely what we found with autothermal biochar is that those effects were highly varied with both the feedstock, so whether that was the corn stover, the iron impregnated corn stover, or the yellow pine, and the application rate. So we know both the feedstock and the application rate can impact both plant growth when the disease is not there, and then when it is there as well. So without the pathogen, baseline plant health performance, we found that the autothermal biochars can increase root length, but there's an associated trade-off of decreased plant height. And then biomass largely had no effect besides the high application rates of yellow pine. When the pathogen was present, we found that corn stover-based biochars increased disease severity, and they also altered the soil pH. So if you remember, corn stover raised the pH, iron corn stover dropped the pH. And then intermediate yellow pine rates, and intermediate being 30 grams per kilogram, that rate was very comparable to the control, meaning that there was largely no difference between the control and that amendment rate of yellow pine. And we also found that soil pH was largely a little bit more stable than the other feedstocks. Moving into digestate, without the pathogen, we found that root length and biomass can be increased with increasing application rate. But then we found that with the pathogen, there's a nonlinear dose response, which appeared with marginal suppression at low rates and then a quick and swift exacerbation at higher rates. And so again, what I mean by that is that the 10 gram per kilogram application decreased just numerically by a few percentage points the root rot, but wasn't statistically different from the control. And then from there, disease severity started to be exacerbated at those higher rates. And then what we found with that is that same 10 gram per kilogram application that just marginally decreased root rot had a significant increase in biomass. And then our field soil experiments. So I just want to emphasize this was not in the field, but soil taken from the field. And we found that the combo of digestate and biochar work better together in the fact that they increase growth all around. When the pathogen is present, though, digestate applied at a 10 gram per kilogram amendment rate showed modest growth promotion. It wasn't, again, we found no effect of any treatments on disease severity, but we did find that marginal promotion of the 10 gram per kilogram digestate when the pathogen was there. So on the left, I really just wanted to showcase this. I think it's a beautiful picture, again, showing this Sievers family farm there and its operation. And I'll kind of just close out here and say that I think, the novelty in what we've been working on in these experiments is largely to date, in terms of circular bioeconomies, not a lot of people have looked at the integrated plant management side of things or the disease side of things. And so we're really excited to be able to push this a little bit further and add context to circular bioeconomies, to add this integrated pest management and to add these disease scenarios, to further be able to add benefits to all farmers and everybody operating within this circular system. And then also I would like to emphasize just this idea, we're really starting to showcase that we could and potentially reduce agrochemical dependency using digestate. And so could we use that same kind of valorization or utilization and use that energy into integrated pest management? And can these products inform how we deal with diseases on a landscape level. So there's tons of work to be done in this point. We are only doing small works, and I think we found a lot of associated trade-offs. Not everything is beneficial, but not everything is bad either. And so I think to set this foundation and start the conversation about how we can integrate these plant disease management opportunities into an agricultural circular bioeconomy is both novel, but really exciting to me. And finally, I'll just kind of conclude and say we found that autothermal biochar and anaerobic digestate increased early soybean plant growth and plant health. With that, though, we found associated trade-offs, including increased disease severity and adverse growth responses. So we know before any of this can be applied on at large scale onto working in agricultural lands, we know that we need to start more research into feedstock and application rates because we know how important they are and how those correlate into the field are going to be vastly important as this project and whole industry unfolds. So overall, we found that this finding highlights the need for longer term and field scale studies to really start to evaluate what's going on here and how can we use these products for benefit and that they don't detriment any of our crop production and resiliency. So with that, I'd like to just acknowledge Rewa Siblani and Drake Oswald for their help with the experiments, and then to all of our funders, and would also like to open it up for questions at this point. So thank you, everybody, for listening today, and had a great time.
Thanks, Brady. If you want to go ahead and click through the next few slides while people get their questions submitted in the chat, which is now available. So thank you for all of you that already have, and feel free to keep entering those. If you attended today's webinar and would like to receive a CCA continuing education unit, please email Alena Whitaker, that's ALENAW at iastate.edu by 5 p.m. today. Please provide your name and your CCA number. And if you happen to watch today's webinar under a different name or than you have registered with the CCA organizations, please provide that as well. And we will get that submitted on your behalf. All right, and I believe our next one is encouraging you all, if you have not already, to complete our voluntary demographic survey. As a USDA-funded program, we appreciate everyone who has already submitted your response. You only need to do one for the calendar year. So if you've already completed it, again, thank you. If you have not, you can either quickly scan that QR code or simply visit iowalearningfarms.org/survey to fill it out. It should take you only about 2 minutes. And again, thank you to everyone who's already done so. All right, next one is for next week's webinar on Wednesday, February 11th. We have Dr. Stephen Hall and Haroam Yadav, who are at the University of Wisconsin-Madison, and they're going to be discussing the underappreciated role of soil organic matter in protecting water quality. So be sure to join us next week for that. And I know we've got a couple more slides, including where you can find this recorded webinar and all previous webinars. So you can visit our website. We have a big webinars button. You can click on that or visit iowalearningfarms.org/webinars. We also have them sorted by topic and year on our YouTube channel. So again, simply search Iowa Learning Farms webinars on YouTube and you'll get directed there. And I'd invite you all to join us next Thursday at 1 p.m. So slightly different day and time, but this is going to be a virtual field day. We're thrilled to have Carl Kurtz sharing with us over 50 years of prairie establishment and management experience. So please join us then. You can find more and register for that online event on our events page at iowalearningfarms.org. All right, so we made it through those, and I know that there's a lot of questions that have come in the chat. So the first one was kind of back towards the beginning where you're talking about a 2% soil health threshold. Could you explain kind of what that means in terms of the organic matter?
Yeah, so like I said, that wasn't a study I worked on. I really brought it in just to highlight the work that was done previously and to add some context. My understanding is that there's kind of this threshold that they consider there's this threshold of soil organic carbon that they consider healthy. And so what that threshold is 2%. So for example, a lot of the carbon and soil at that farm started at 1.7%, and they found after years of application that it started to go above that 2% threshold. Now, I'm not sure exactly what went into calculating that 2% threshold or what that's made of or how it was decided, but that's my understanding of what came out of that.
Ah, okay. So what do you think are some of the mechanisms for either beneficial or harmful effects with each amendment?
Hmm. Yeah, so there's pretty good literature out there showing that fixed carbon has a lot to do with the impact of diseases. And so what I mean by that is there's three fractions of biochar. There's the volatile matter, there's the ash, and there's the fixed carbon. So the way I think about it is ash and volatile matter are like dusty. They're very dusty. If you were to touch it, all your hands are going to start to turn kind of that black color. Versus fixed carbon is the more recalcitrant carbon compounds or aromatic compounds in the biochar. And so what we find, and at least what I hypothesize, is that the corn stover based biochars are high in ash and volatile matter, meaning that those materials and functional groups can disassociate within the soil matrix very easily, meaning that the pathogen can, of course, use that carbon for its own fungal metabolism. Versus with the yellow pine, it has a higher fraction of fixed carbon content, meaning less functional groups around to disassociate into the water, and not water, but soil matrix, leading to potentially just less stimulation or fungal stimulation growth. So that's one mechanism. The other, and that's a little bit more chemical based. I would say the other ones are a little bit more physical. So biochar and digestate both have proven in terms that they can alter bulk density, soil structure, aggregate stability, things like that. And I think all of those physical properties, again, translate to disease outcomes because, of course, compacted, cool soils is going to allow this to proliferate more. So if we have, a soil amendment that can, help with the bulk density and all those other things, should be able to help manage some of these disease outcomes.
And thinking, so you did all the mixing for your greenhouse studies, but on a field scale application, is there tillage involved to incorporate these, or are these surface applied applications?
Yeah, so it depends, and it's pretty nuanced. For the digestate, they can either do liquid or solid. So at the commercial farm we work with, they do both. So they inject liquid, and then they broadcast apply the digestate, the solid part. And then with the biochar, a lot of times what I've seen is broadcast spread, or they can kind of sometimes till it into the ground. A lot of times the problem upon application, you can imagine, is if you are throwing a whole bunch of biochar, there's going to be these huge black clouds that come out of it. So a lot of times what I've seen is they'll water it down or wet it and then broadcast spread it from there.
And speaking of the biochar, what is the estimated cost of producing or if you were to actually go out and buy it, um,
Mhm.
what would that look like?
Yeah, I wish I could give you, a legit quantifiable number, which I hope I'm going to take away from this presentation and find out exactly how much. What I do know is that biochar is expensive. So currently, the economics surrounding the supply chain are still being worked out to make it economically viable for farmers. So generally, what I would take away is that as of right now, it is expensive to purchase because the supply chain is still being built around it and that circular bioeconomy part. But I will definitely know for next time how much biochar costs. That's a good question.
And I guess that ties into, so you were working with the BioCentury farm, but if people wanted to go out and buy it, is it commercially available?
It is. So there are, I actually have done some work before this using some different biochars that were more conventional, and we got them from various different businesses actually in the surrounding area. So I think the one I'm remembering off the top of my head is like Artie Biochar. So they produce biochar, and you can purchase it from them. Also, someone here at Iowa State, Dr. Shantanu Bashki, who I met earlier, is starting a biochar slow release fertilizer startup. So I'm not sure where they're at with that. May not be able to purchase it yet, but the direction of the industry is definitely headed in. So the ability for to be economically viable.
And so you discussed that when you switched to the field soil, you started counting root nodules. Are they an important metric for soybean health? And possibly what might be some of the causes for the lack of root nodules when you used the sterile soil?
Yeah, so the second part of that I can answer pretty quickly. Pasteurized soil, what we use is a 2-to-1 sand soil ratio. So a lot of times we either have to add a fertilizer to be able to get the proper nutrients in that soil system. So what we do know is that soil is largely just has limited nutrients. So that's why we see a lack of kind of root nodule development, where in the field soil, especially where the plots I got it from, are very fertile. And so that's why we start to see those root nodules. Now, is it a plant? Is it an important plant growth metric? That can be taken in many different ways. It just depends. I would say if I'm talking to a farmer, I would say, is this product worth adding on 50 more root nodules to you? And allowing them to make that decision. I would say I'm glad we quantified it, and it definitely has something to do with the nutrient recycling in the rhizosphere. And I wish I knew a little bit more about the development of those root nodules. But I'd say, yeah, most definitely seeing more is a good and positive thing. But does that translate to any increased yield or economic kind of accruity? We don't know. And so, that's just up to the farmer at that point to decide if he wants 50 more root nodules or not based off these treatments.
All right, a couple more questions here. Um, so were soybeans inoculated with rhizobium in the greenhouse studies?
They were not.
Okay.
Nope.
Did you analyze any sort of like additional plant nutrients additions that you got at your different application rates? So looking at other, besides maybe nitrogen, phosphorus, potassium, all that. Did you look at a panel of other nutrients in those digestates and biochar?
Yeah, we didn't specifically look at our digestate. We did at our biochar. So our biochar, we did carbon, hydrogen, nitrogen, and sulfur, and then of course the volatile matter, the ash content, and the fixed carbon, which are kind of the most important things. And so we did analyze that nutrient. So I'll kind of re-show that the yellow pine had that high recalcitrant fixed carbon, where the corn stover based biochars had a more ashy material, something more dusty. Now, with the digestate, again, this is being applied on the commercial farm. So there's a lot of people that have done a lot of work into what is in the digestate. So in that paper I showed, you can actually go to a table in there and it'll break down over the past 10 years, what are the mean values of nutrients that this farm is getting. We specifically, in my lab, we did not do that, but we do know that digestate has a high fraction of ammonia available. And so that would be one thing I'd want to take away there. And also phosphorus. Sometimes it can leave quite a big trail of residual phosphorus in its wake.
Did that paper also discuss any contaminants that were in the digestate as well as the nutrients?
No contaminants it discussed. There has been some stuff in the literature to suggest that some pathogens can survive the anaerobic digestion process. But what they largely found was back to that phosphorus. So although they found these like super big incremental soil organic carbon accruals, there was a little bit of a trade-off there in that they started to find saturated amounts of phosphorus. So potentially maybe, the biochar could be integrated to help absorb some of that.
And then I'll kind of wrap up here, but outside of anaerobic digestion, what other industrial process might help produce some of that digestate? Or is that
Hmm.
primarily a product of that process?
It's primarily a product of that process. And there's a few different types of or pathways, we could talk about. There's things like gasification, methanization, all these different things. And I'm a little ignorant to that side of things, but to me, these are the two main processes. And I would say these are the most relevant ones. You could think of like ethanol. The ethanol industry was kind of the past in a way, and this is kind of the new way of thinking about that. So maybe ethanol industry is maybe another pathway we could think about. I know there's been some work into grass into ethanol and stuff like that. But overall, this is kind of pushing the needle a little bit forward with new pathways and industries.
Well, thank you so much, Brady, and I look forward to helping celebrate your upcoming graduation. And thank you for sharing this, and I hope you all can join us in future weeks for our webinar series and next Thursday for our virtual field day. Have a great afternoon, everyone.